knows a lot about the science stuff. Professor Dave explains.
This is CERN's visualization of the standard model of particle physics. It shows the quarks, leptons, and force bosons, as well as the Higgs boson. But this is also the standard model of particle physics. It shows the quarks, leptons, and bosons, but in a more mathematically rigorous way that contains all of the quantum field theory information and mathematical structures that we discussed throughout the tutorials on symmetries, QED, QCD, and the weak interaction. This equation is called a Lagrangian, which comes from Joseph Louis Lagrange's reformulation of classical mechanics known as Lagrangian dynamics. A simple way to think about a Lagrangian, written with an L, would be to set it equal to the kinetic energy of a system T minus the potential energy of a system V. The Lagrangian comes from the principle of least action, which says that the path taken by a physical system between 2 points in time is such that the action S, defined as the time integral of the Lagrangian L, is stationary, meaning a minimum, maximum, or saddle point with respect to variations of the path. From the Lagrangian, the laws of motion for that system can be found. These laws are written as an equation that describes the behavior of objects in a system as a function of their positions and momenta, and it comes from plugging the Lagrangian into the Euler-Lagrange equations. In classical mechanics, the formula for the Euler-Lagrange equations is the derivative with respect to time of the partial derivative of the Lagrangian with respect to q dot with index I, using the notation of dot being a time derivative, is equal to the partial derivative of the Lagrangian with respect to q with index I. Because there are 3 spatial dimensions, index I can be either 1, 2, or 3, and q corresponds to a generalized position coordinate such that q dot corresponds to a generalized velocity coordinate. In each spatial dimension, there is a separate Euler-Lagrange equation that governs the motion of objects in the system. You may have noticed that we said this picture was a Lagrangian density, not just a Lagrangian. When we move from classical mechanics to field theories, the Lagrangian density becomes a more useful quantity. It can be defined using the relationship that the Lagrangian L is equal to the integral of the quantity called the Lagrangian density, denoted with a cursive L over all space. This reflects how the natural quantity for fields is a density, since fields are defined at every point of both space and time. From the Lagrangian density, the so-called field equation can be written. This is an equation analogous to the classical equations of motion that describes the objects and energy within a given quantum field. As a result, the Lagrangian density is often used to express quantum field theories. For the Lagrangian density, the formula for the Euler-Lagrange equations is the partial derivative with respect to mu of the derivative of the Lagrangian density with respect to the derivative with respect to mu of phi index I equals the partial derivative of the Lagrangian density with respect to phi index I. Phi index I is the quantum field, which can have n dimensions, so I can be any number between 1 and n. We can see that this looks somewhat like the classical Euler-Lagrange equations, but involving a derivative with respect to mu instead of time. If mu can only equal 0, the time derivative, this looks very much like the classical version. However, we must account for all of spacetime, so mu can equal 0 for the time derivative, and then 1, 2, or 3 for the 3 spatial dimensions x, y, and z. Now that we know what a Lagrangian density is and why it's useful in quantum field theories, let's look back at the standard model Lagrangian density. The first section describes gluons, the second section describes the other bosons, the third section describes the weak interaction, and then the fourth and fifth sections describe virtual particles in the Higgs field and the weak interaction, respectively. This is an extremely complex equation, but CERN has written an article to help break it down into a more simple and digestible form, which is linked in the description. Using Lagrangian densities, scientists can use math to demand that field theories are gauge invariant under certain transformations that the physics dictates. This is how the Lagrangian densities of the standard model can be constructed, to obey the electroweak gauge symmetry of U1 for electromagnetism and SU2 for the weak interaction, and the QCD gauge symmetry of SU3. Each of these symmetries corresponds to a specific mathematical operation that leaves the Lagrangian unchanged, hence gauge invariance. Using the Lagrangian densities for these field theories, the Feynman rules that we discussed in previous tutorials can also be derived to do calculations with Feynman diagrams. It seems like these Lagrangian densities can be simply written down and used to build the entire standard model. Well, almost. There is one major issue. The gauge invariance required by the standard model puts a big constraint on the kinds of terms that are allowed to be written in these Lagrangians. If mass terms are explicitly inserted into the equation, gauge invariance can be broken. We know that the gluons and photons are massless, so this isn't an issue for them, but the W and Z bosons must be massive for electroweak theory to work. Yet gauge invariance must also be obeyed. This means that there has to be a way to identify and define mass terms within the Lagrangian, even without explicitly writing them. This is where the concept of spontaneous symmetry breaking comes in. Imagine you're holding a flexible plastic rod. This rod is symmetric and in its ground state, so to speak. Now imagine applying a small amount of pressure to either end of the rod, like a small perturbation. The rod will bend in one direction, creating a curve. The rod is no longer symmetric and has spontaneously snapped into a new ground state. However, the direction in which it buckled is completely arbitrary. It could have done so in any direction, because the initial setup was perfectly symmetric. In this simple example, the symmetry has been spontaneously broken by the random and arbitrary choice of a new ground state that effectively hides the initial symmetry. The word spontaneous refers to the fact that the equations of motion within the system don't specify how the symmetry is broken, but rather it's the system itself, not the underlying rules, that chooses how the symmetry is broken. This is directly analogous to the spontaneous symmetry breaking that takes place in quantum fields. Initially, the field is resting at a minimum of the W-shaped potential. This is a 2D representation, but you can imagine it in 3 dimensions. Then, as a result of some sort of perturbation, the field rolls down into a new ground state, or vacuum state, along the brim of the potential. However, the direction that it breaks in is spontaneous. It could have broken in any direction. Now that the field is in its new ground state, it does not see a symmetric potential U, while the overall symmetry is still preserved. Mathematically, we can conceptualize this by having two fields, phi1 and phi2, in a potential density, defined similarly to Lagrangian density. This is expressed as cursive U equals negative 1/2 mu squared times the quantity phi1 squared plus phi2 squared plus 1/4 lambda squared times the quantity phi1 squared plus phi2 squared quantity squared. This has a corresponding Lagrangian shown here, where the part in the brackets is kinetic energy. Let us now define new fields. Eta, which is defined as phi1 minus mu over lambda, and xi, which is defined as phi2. This redefinition doesn't break the symmetry itself, but it reflects the fact that the field has chosen a specific vacuum or ground state, making the symmetry breaking manifest in the math. If we write a Lagrangian and plug in the newly defined fields, we see the following. 1. A Klein-Gordon Lagrangian for the field eta, which corresponds to a massive field, with a mass dependent on the parameter mu. 2. A free Lagrangian for the field xi. 3. Coupling terms that describe couplings between the fields eta and xi. 4. A constant offset. This Lagrangian is clearly asymmetric, so we have successfully mathematically produced the spontaneous symmetry breaking. The symmetry of the original Lagrangian has been broken, and we have gained a massless boson in the process, the xi field. This is known as Goldstone's theorem, which says that the spontaneous breaking of a continuous global symmetry always produces a massless scalar boson. These are known as Goldstone bosons. This spontaneous symmetry breaking is remarkable, but it hasn't explicitly solved the issue. Instead of giving mass to the W and Z bosons, the symmetry breaking just created an extra massless boson that we had not seen experimentally. Thanks to Peter Higgs, there is a neat trick that can be applied to solve this issue. Higgs saw that he could rewrite the Lagrangian in terms of one combined complex field phi, which is defined as phi1 plus I times phi2. By doing this, Higgs realized that if you promote the symmetry from global to local, allowing the symmetry transformation to vary from point to point in space and time, then the theory naturally includes gauge fields. And through a clever choice of gauge, this had two crucial consequences. It removed the massless Goldstone boson term and added a massive gauge field term. Essentially, through what is known as the Higgs mechanism, the massive gauge fields containing the W and Z bosons are effectively generated by absorbing the Goldstone bosons produced during spontaneous symmetry breaking, and another massive boson field is created, known as the Higgs field of the Higgs boson. The potential famously associated with this Higgs mechanism spontaneous symmetry breaking is often called the Mexican hat potential. It's essentially just a 3D version of the W-shaped potential we saw earlier. This mechanism that occurs during electroweak symmetry breaking explains how the W and Z bosons get their mass, while adding one more boson to the standard model, the Higgs boson. We now know how the W and Z bosons get their mass, but what about the other particles in the standard model? This is where Yukawa couplings come in. These appear as terms in the Lagrangian, which mathematically represent the Higgs field coupling to the different fermions in the standard model. Each fermion couples to the Higgs with a different strength, and their coupling strengths are directly related to how massive the particles are. Scientists began to search for the Higgs boson, which lasted for decades. While they couldn't predict its exact mass due to its unknown self-interaction strength, they knew how it should decay and that it should be short-lived and electrically neutral. Finally, in 2012, the CMS and ATLAS collaborations at CERN announced that they had found a particle that appeared to fit all these criteria. They only had to check one more thing. Was it a boson? Was it spin zero? In March 2013, they proved that this was the case, and the Higgs boson was officially added to the standard model. Peter Higgs and Francois Englert were awarded a Nobel Prize in 2013 for the theoretical work leading to the discovery of the Higgs boson. To this day, scientists are studying the Higgs boson's interactions and decays with other standard model particles. But what else are scientists around the world studying to continue to probe the standard model, and how do they observe all these mysterious particles? The next tutorial will cover precisely this.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.